Hi, this is Dr. San Abdullah with the course Complexity Analysis of Algorithms. So the topic which we are covering is graph algorithms, and the subtopic is tree traversal. So this is the fifth topic, so lecture 5, and D is the subtopic, which is tree traversal. So this course uses the platform of ezmcq.com/GoGet, which basically is a learning management system, but it is a personalized learning management system. Personalize the required level of learning, which you can see in video number 1. And then there is the personalization of the experience also, user interface as per your liking. That's video number 4. And you can have your personalized exams and their testing, grading, and analysis. So you have grading, testing, and analysis, all of this stuff. So if you go to YouTube and type my name, Dr. Sanadullah, it will take you to my YouTube channel. And there you will see all these 6 videos to use this tool and this learning management system, and you will also find all the videos of all the courses including this analysis of algorithm. So let's look at the outline of this wonderful course. So this course consists of 11 topics, and this consists of the latest content, not old content. And right now we are at topic number 5, which is graph algorithms. So let's now move on to the learning management system, which is the supplemental website. So we are at the learning management system, to be very precise, personalized learning management system. So we are looking at the tree traversal. Now remember that this search over here, this is not the search while we are looking for something. Basically, this is a traversal. Search is a separate topic in this course, and in which we'll cover binary search, we'll cover hashing, and so on. So this is not the search, which this is not in the literal meaning of the search. So what does the breadth first search does is that, of course, it is an algorithm, so it will find the result, and it works for the unweighted graph, and there are certain properties, and we look at the space and time complexity. So what is the special feature of breadth first search is that it explores a graph level by level. Basically, it's a tree, because otherwise it will create problem by of course it could be graph also, but then we have to something called as the back edges. So we have to avoid back edges which create the cycle. Anyway, so it systematically visits all the neighboring nodes at the present level, current level, before moving to the next level. So it traverses the structure level by level. Okay, and useful for finding the shortest path in an unweighted graph. So that we are counting the number of edges. So these are the steps. This is just standard steps. Nothing special can be seen here. The special is the BFS properties. The properties are its completeness. So it is guaranteed to find the shortest path. This is the beauty of it. Guaranteed. That's an algorithm. And it explores all nodes at the current depth level before moving to the next level. That is the property. And unweighted shortest path. It works with unweighted graph. All right. It could be tree also. And time and space complexity visits each vertex and edge only once, so there is no repetition. And the time complexity is order v plus ev is the number of vertices and e is the number of edges. Now this space complexity is the additional space for storage of the required queue and the visited set. Okay, this is not, so there's additional space of storing the graph itself. Okay, so demonstrate the working of the breadth first search. Okay, we'll do that. So these are the steps which we looked at in the previous question. Selecting a starting node, okay, which is also called as a root node, and the queue is placed in a data structure. The starting node is placed in a queue, all right, and then start exploring the neighbors of the current node, one level at a time, level by level, okay, and then visit all the neighboring nodes at that level which have not been visited. And once it is done, it enqueues those neighbors into the queue if they have not been visited before. So one level, then discover the neighboring nodes, and thus moving level by level, and marking the visited nodes so as to prevent them exploring again, and to avoid infinite loops. Okay, don't want that. And when does it terminates? Okay, it terminates until all nodes reachable from the starting node have been visited. When all nodes have been visited, it terminates. So what is the output? The output or a process is how it is shown. Let me, it's okay. So depending upon the specific application, so it could be a path also, or the traversal, order also. So we see here that this is how it works. So this is one level, then is another level, then is another level, and then so basically starting node, then A, B at one level, C, D, and G, H. C, D, and G, H is another level, and then E, F, I. E, F, I is another level, and then we finally have K. So this is level by level traversal on a breadth first search. Now the breadth first search also has its strengths and weaknesses. So strengths are it guaranteed the shortest path in unweighted graph. Okay, it's very simple to implement and understand. And it's a complete algorithm. Complete means that find a solution if one exists. Okay, as long as the graph is not going to connect with connected components. Okay, or forest, and works well for finding. And of course, it can also find connected components. Okay, for example, for network analysis, for social network analysis, social network modeling, and so on. So what are the weaknesses? It requires significant amount of memory to work with, especially for dense graphs. Okay, and it can be prohibitive for large graphs. Again, there are too many vertices, and does not works for weighted graphs, which we come across A star in AI and Dijkstra algorithm, which Dijkstra algorithm can find single source shortest path optimally and slower than depth first search. Okay, slow. And I'll show you, and then you will understand how it's slower than depth first search. Time complexity is same as the breadth first search. All right. I'm sorry. The time complexity of breadth first search is order V plus E, which is also the case for depth first search, and requires order V additional space. So these are its limitations. Okay. So let's move on to the next question. So what is depth first search? So depth first search. These are the definition and properties. Let's look at them. So explores as far as possible along each branch before backtracking. So if you want to know about backtracking, go to easymcq.com/goget and you type in the yellow box backtracking and you'll get some stuff about backtracking from there. All right. So so explores as far as possible along each branch before backtracking. Okay. And it can be implemented using a stack or via recursion also. Okay. And it is what is the application pathfinding exploring connected components in a graph. So these are the steps, and we will look into these steps in detail when we look at the detailed working. So it is depth first is not guaranteed to find a solution in finite time for all graphs. If graph has cycles or infinite paths, then is a problem. It will go into an infinite loop. Okay, unless cycle checking is implemented. So whenever it visits, you look at is there an edge between the vertex which is currently visited and the one before visited. So if there is an edge, then it's a cycle. And it does not guarantee the shortest path in an unweighted graph. So it has its limitations for unweighted graphs also. Space uses less memory as compared to breadth first search. Okay. Why? Because it is only storing a path from the root to the current node. Okay. And of course, there's a cost of recursion also. All right. So what is backtracking? Backtracking is explores nodes deeply and backtracks when no unvisited neighbors are found. So it is good for maze and puzzle solving games. All right. Time and space complexity, it is same. Order V plus E, it is same. And this is OV because in the worst case, because as I mentioned, recursion can be a problem. And what are the problems with recursion? We've already covered in topic number 3. So demonstrate the working of the the depth first search. So you see that we don't have the properties. We have something new here, which is backtracking. If depth first search reaches a dead end, okay, with no it backtracks. Okay, so this is the recursive call. So that can be slow, and it continues the exploration process and prevents revisiting some node multiple times, so that avoids infinite loop. Same for breadth first search also. And the process backed until all nodes are reachable from the starting node. So we have the right node and then the root node and the left node. So let's look at the example. Okay. So you see, it is not going level by level, but it is going vertex wise. It go keep on going, and keep on going, right? And then it backtracks. Then it gets backtracks. Okay, this is how it works. So it's a different thing as compared to the depth first search. So what are the strengths and weaknesses of the depth first search? one thing is same, it is straightforward to implement, iterative, okay, and it could be a recursive approach also, then we use a stack, right? And memory efficient for uses less memory as compared to the breadth first search, because it keeps on going and then it backtracks, as opposed to breadth first search, which has to goes level by level. And good for pathfinding and connectivity, suitable for backtracking, for solving mazes, puzzles, combinatorial problems, and queens problems. So basically, it when it backtracks, okay, it backtracks, and then of course it is non-exhaustive. Okay, it backtracks, so explores one path fully before attempting the others. So more similar. Okay, so used for cycle detection, using the edges. So what are the weaknesses? The weaknesses are as follows: does not guarantees the shortest path between two nodes, between any two nodes. That is not guaranteed. Okay, and may miss a shorter path than a breadth first search, because the breadth first search is more exhaustive. It's going level by level, and may get into infinite loops for directed graphs. So we have to be careful when it can be used, and not very efficient for dense graphs, unnecessary exploration and less efficiency. High space complexity for deep graphs. Deep graphs means that the distance from the leaf to the root is very high. Okay, and then of course lack of completeness in infinite graphs. Okay, so if you want to read more about it, here are the references. So now we will finish this topic with animation, and you look carefully, the difference between the depth first search and breadth first search will become very clear. So here are the animations. So see, depth first search goes all the way, and this is going level by level, right? So that's all for this topic. Thank you very much.